We don't have a light for it. I can see them here. So, good afternoon, everyone. Thank you for coming to this one of this last session of the day. I will share with you the work we've done during the Lotus project on calibration transfer. This was work done in collaboration between Université Gustave Eiffel, Indian Institute of Technology, Guwahati in Assam, India, and IMS Bordeaux in France as well, and Université Gustave Eiffel, my university is in Paris. So I'm Berengere. The work was done mostly by Bala, who is in India and couldn't travel. So we worked on the assessment of 10 standardization-based calibration transfer techniques for gas sensors in a small data context. So this was published last year in the IEEE Sensors Journal. So you probably know the impact of air quality and water quality in terms of death. You probably know this number. There's a general consensus that if we had environmental monitoring, it would be a good thing, provided the data of environmental sensor is of good quality. The quality of environmental sensors data is not guaranteed as of now. And for it to be good, you need a good calibration. And you need this good calibration at a low cost. If you look on the internet, the cost of calibration, it's not so easy to find number of how much calibration is going to cost to a sensor. I found this paper from IEEE Transaction and Instrumentation and Measurement in 20 years back, and it gives this number. Basic calibration is 100,000. Automated calibration is $1 million. And I think this number remains in the good range of magnitude. It's a huge number because this number then are spread on all your devices. So if you're selling devices, your sales cost includes this cost of calibration. What happened is that in practice, a lot of sensors are sold with no calibration, and the calibration is done on a couple of sensors of the batch. This works very well for temperature sensor, for strain gauges. This works perfectly. It doesn't work at all for environmental sensor. No way, no how today with present status of the technology. So you're back to calibrating each device one by one, which is very expensive and brings up the cost. And it brings us today the cost of the environmental sensor by a factor of 10. I'm talking from parents, okay? The concept of calibration transfer is that instead of calibrating all sensors, you would calibrate one sensor fully and expensively, and then you would do only a small number of experiments on the other sensor, use algorithm, calibration transfer algorithm, to get a good calibration for all the other sensors. Question is, does it work? This is a technique that was originally developed for spectroscopic instrument. You needed to calibrate the response of a spectroscopic instrument for each frequency of the instrument. And it started being applied to environmental sensor and sensors arrays in the last couple of years. And the idea of this paper is was originally to check the applicability of this technique for the sensor array developed in Lotus project. And so we did numerical tests on the problem. So maybe you don't know about calibration transfer, so I'm going to do a brief summary of what it is. You have three methods of calibration transfer so far. As a definition, what I call output of a sensor is the raw data. Like the raw data is the voltage or resistance, it's the output, and the target is the temperature for resistance, or it's the gas concentration. That's what I call target in the rest. So either you standardize the output, meaning that you bring the output of your secondary sensor, the one you don't want to calibrate, you make it look like the primary sensor, and you make the response look like the response of the primary sensor. You can do output standardization. You calculate your target of, you calculate the target through a secondary calibration model, and then you do standardization of your target, okay? And you can update the model. So you have three approaches. The present paper deals with response standardization. And we did a state-of-the-art of application of this technique to sensor arrays. So this what you can find on the paper. The technique that have been reported used on sensor array. One challenge that underlies all this work is you don't have much data, because it's very hard to have big data set with sensor array. Datasets are usually small, so there's a lot of techniques that would work with an infinite volume of data, but doesn't work in a small data context. In the rest, I will talk about transfer standards. These are the data, the target that are common to the primary and the secondary sensor. You need these guys to be able to do calibration transfer. You need to have common points that are known for both the primary and the secondary sensor to do standardization. So very briefly, so that you get a sense of how these techniques work, I will talk about direct standardization, which is the most known method in response and standardization. So basically, I told you you want to make your secondary sensor response look like your primary sensor response. To do that, you do algebra. Basically, you multiply your array, your vector array of response. You multiply it by a matrix, and this matrix is based on the Moore-Penrose inverse, based on the transfer of the secondary transfer standard and the primary transfer standard. The math of that are pretty straightforward, and this is one of the most common techniques. You can do the same thing after having projected the outputs onto the principal component of your problem, or onto the partial least square regression vectors of your problem. Partial least square regression minimizes the correlation between the vector and PCA, maximizes variance. If you don't know, I didn't remember, so I really hope this when I did the slide. And then you do direct standardization. And then these are approaches based on vector, taking the sensor array as a vector of data. There are methods that are based on managing each sensor in the array separately. So you have a sensor array of 10 devices, you standardize each device by either linear regression. So you make a linear regression so that they have, so you look for the coefficient that the linear transformation that brings the secondary sensor as close as possible to the primary sensor one, or you do mean correction. You adjust the voltages, for instance, so that they have the same mean as the primary sensor, even either by addition or by multiplication. We tested on 3 experimental datasets for gas sensor. We tested one dataset with 5 sensing units of the same batch on 4 gases, 22 days, but pretty small dataset. So data was expanded based on exponential model. Time-drift study of 1 sensor, and then these were MOX sensor, metal sensor, and we also tested on RF-based humidity sensor developed at IMS. And 2 sensors were tested, and we wanted to do transfer from the lab to environmental, to the outdoor. We have very classical approaches. Our gold standard is that you want your calibration transfer to be better than recalibrating with transfer standard. Because if you recalibrate with the transfer standard you have, and you don't have better than that, it's pointless to calibration transfer. You just recalibrate your sensor. So that's your golden standard, and your ideal is to be better than that, and you want to be better than the naive prediction to predict the mean. These are the outputs that are in the paper for the 3 use cases. And you have also many tables in supplementary for all the different use cases, number of transfer standards. So, because we studied the performance of the method for different volume of transfer standards for both linear regression and KNN, because we wanted to compare a machine learning technique with a physics-based technique, let's say. So this example here This is our first use case. The primary sensor is the calibration of your actual good sensor fully calibrated. This is the performance that it has. You see linear regression is much better than KNN because there's not much data. Your secondary sensor, if you had a full huge data set, this is what you would get. And if you recalibrate with transfer standard, you find 19 ppm of error prediction for, I don't know which gas it is. Sorry, it's a VOC gas. And then all these guys are your calibration transfer. So you see direct standardization here for linear regression does better than recalibration with transfer standard in this case, a little better, but single sensor standardization does bad, very, very poorly. And a lot of methods here have a very bad R2 -1, R2, it's terrible, okay? We had all this nice plot, and the black line, it tells you your primary model. That's your dream. You have calibration transfer, you do better than the primary sensor. That's your dream. The green line here is your recalibration with transfer standard, and this is what you want to do better than. You want to do better than this green line. So you see in this case, you do a tiny little better for linear regression. You do somewhat better with KNN, but KNN is not really good for this use case. Okay? So I'm not going to bore you with the detail. I'm not going to explain that. I'm going to show you this. This is the conclusion of the paper. It's the 3 use cases, all the method summarized. And if you have a minus, it's doesn't work at all. If you have a plus, it's better than naive. And if you have plus, it's that you're better than recalibration. You see there's not many plus. There are very little plus. There are a couple of plus from time to time, and there's a lot of minus. Recalibration with transfer standard is always a good bet in our case, and it's very often the best bet. I'm sorry to say that it's often the best bet to recalibrate with transfer standard. This is the graphical abstract of our paper. There are 2 methods that we think have good promises in this context, is direct standardization and partial least square. The other one were really terrible in this context. And the conclusion of our paper is it's necessary. I will go to the end. It's necessary to compare the method. It's not automated in the present state of the art that a method, any calibration transfer method is going to work. So you need to compare, and they may not work, unfortunately. In the specific context of this study, all the sensors were exponential. It happened. It was not on purpose. It happened that they are all exponential. Calibrating an exponential sensor needs only 3 points. So that may explain why recalibration works so well compared to other methods. This being said, this is a very common use case. MOX sensors, humidity sensor, it's very common. So the takeaway from this is that test recalibration with transfer standard and then test your method. The single sensor standardization, meaning the method based on splitting your sensor array, did not work. None of them worked. What worked were the vectorial method that worked a little. Direct standardization, partial least square. On that note, I'm done. I hope you understood and that you will have a good afternoon.